Thank you. So there have been a lot of other talks since my last talk, so I'm going to recap quickly what we need to remember. So we defined additive categories A of a metric space, which most of the time is a simplicial complex. And A is some additive category we start with. And the objects were tripled, so we start with a finite set. Then we map the finite set to the metric space and also to the objects in A. Okay, so in other words, an object is just a finite collection of objects in A, but for each of those objects we also picked a point in E. Right. And morphisms were just matrices, so morphism phi is just a collection of morphisms in A between the objects in A. And the only additional information is that for every such matrix entry, we now have 2 points in E, and we can measure the distance, right? And then think about a morphism being small if those points are always close together.
You got 2 pi's up on the first line, the second pi being A.
I have too many primes? Pi's. Oh, right. I called the second one A. Thank you. Pi's. Yeah, never enough pi, but yeah, thank you. Okay. Right, so that was the sort of the easy starting version we had, and then we had a more sophisticated gadget that defined this Petersen-Weibel homology theory. And I'll want to go through the definition again because I want to work with it. So again, we have a set. Now it's no longer finite, and we're mapping to a product. And again, to the objects. All right, so now we may have infinitely many objects, and the infiniteness is accounted for by the natural numbers here. And right, we had a condition, one that I did mention and one that I should have mentioned. So if I look at the preimage, right, if I look what happens over a point in the natural numbers, it's supposed to give me back this. So this is supposed to be finite. Pardon? Yes, I mentioned that, but now there's another one that I didn't mention. Okay, so, and this actually a little, yeah. So I also need a condition on, I mean, it's not a terrible condition, but I want the image in E not to be to spread out too far. So I want this to be contained in some finite dimensional subcomplex. Okay, so uniformly, I mean independent of n. Okay. And then morphisms were matrices again. So it's just the same as above. Only that now the matrices are infinite. And we can ask for more interesting conditions. And those were first, I don't want to move in the direction of the natural numbers too far. So if pi n of s minus pi prime n of s prime is bigger than alpha, then the matrix entry is supposed to be 0. And the other condition was that if we move towards infinity, then in the E direction, the matrix entry should only be non-zero if the points are close together. So for all epsilon, there is an n naught, such that if pi n of s is bigger than n naught, and the distance in E between the pi e's, if that's too large, then again this is supposed to be 0. Okay, and then we introduced equivalence relation. We said phi morphism is equivalent to psi if they're the same for almost all S and S prime. Right? We were allowed to forget to find number of things, and the picture was like this. In the beginning, the morphisms can do anything, at least in the E direction, and later on, they look almost horizontal. Okay, and so okay, right, and then the Farrell-Jones conjecture became the statement that if we put in this classifying space and now use the action of the group to form this group ring construction, then the map induced by projecting on a point let me not write down the alpha. Right, so this is the map induced by just projecting the space to a point, and that is the assembly map. So the Farrell-Jones conjecture is that this is an ISO in K-series. Okay, and that's what we need to prove. Okay, but one nuisance about this was that there is a shift. So Kn of this is Hn minus 1 of the homology theory we're interested in. Right? This is a priori not a problem, but it makes arguments sometimes not as natural as some would like them to be. And so at first I want to do a variant of this where that helps to get around problems that arise from this shift. Okay, and the trick, I mean, the way it works is we're going to define a subcategory just kind of called D0, where we strengthen, so everything is the same, but we strengthen this condition here by requiring it for alpha to be 0. So whenever the n entry is different, then the matrix entry is supposed to be 0. Right, so now the picture looks like this. I mean, morphisms can only go up and down, and as we move out, they can only go up and down a little bit. Okay, so the condition is, let me spell it out. The condition is if pi n of s is not equal to pi n prime of s prime, then the entry is supposed to be 0.
So now it's really a subcategory of the product.
Exactly. So right. So this becomes a subcategory of the product of the AE. Well, not quite, because we have this equivalence relation. So it becomes a subcategory of the quotient of the product by the sum. Okay? And again, and this is also a homology theory. It's just that its coefficients are messy, because this trick we had when we computed, well, I mean, the swindle we had when we computed what happens on the point is no longer going to work. Right? We can define, right? We can define the functors in the swindle, but we can no longer identify Fn and Fn plus 1, because that involves shifting ones to the right. Okay, so the values on the point are going to be a huge gadget. It's basically the product of the K-series by the sum of the K-series. So a nasty thing, but so there is diagram that relates them. Yeah, right. So I have 3 times the D0 guy and 1 times the actual guy, and this is push out in K theory. Okay, so there's my Vitor sequence that computes what we're interested in terms of these zero guys, and in particular, if we have this for the d0 guy, then we still get the Farrell-Jones conjecture, right? Because then we get the corresponding statement for E. Yes?
The lower left should really supposed to be a D0 or something.
So these are 0, 0, 0, and this one is D. It's just one D.
What's the difference between the upper left and the lower?
Oh, well, sorry. Those three are all the same. The functors are, they're not the identities. Yeah. So, maybe I briefly say in words how the functors are. So, we pick a sequence of points in the natural numbers that have larger and larger distance, that is more sparse and sparse, and then you color them in 2 colors. I mean, white, black, and use the white points here, the black points here, the white and the black points here, and then you map 2 points onto 1 point, but you have sort of 2 ways to do this. You can map a black and white together to a point here, or white and black to a point here. This kind of glues it together to a line. Okay. Okay, so this is, I mean, it's not terribly difficult, but it's convenient to have this. Pardon? Oh, the other 2? Those are the inclusions. These are the inclusions. I mean, these are the maps I explained to you, yes. The sparser and sparser, right? I mean, think about this sparser and sparser. If you take the sparser and sparser stuff, then you can think of this as a subcategory in here, right? Because then this requirement that we added here becomes automatic, because now, right, we only allowed natural numbers that are further and further apart. So by this condition, by the alpha condition, where is it? This one here. Eventually, this has to happen on this subcategory. Okay. But anyway, so it's just a matter of convenience, I think.
So in your bars, you want the lower left quant to be D0 instead.
Pardon? This is D0. Oh, everything is D0 but this one. Huh? Okay. Okay. So now I want to talk about functors going the other way, and it's going to be more easy to do this on the D0s. Okay. So I want to go backwards, and let me start slowly. So there's the Swan group that talks about such functors, and it can be constructed from, as the case here, of a category, and that's just the category of finite rank free abelian groups, together with an action of the group V, right? And then morphisms are, what they're obviously going to be. But I want to think of this slightly differently. This is the correct definition, but I want to think of this a little different in order to make things more natural later on. So if I have an action of G on an additive category, then we discussed this kind of category here last time. Okay, and this is some kind of homotopy quotient of A by G, right? Because in this category we just added isomorphisms from GA to A, right? Namely the one that we would call the identity of A times G. Okay, and now I want to do the same thing with fixed points. Okay, so the objects are objects, but there's supposed to be fixed under the group action of G up to isomorphism. So we're just going to trivialize the group action. So meaning we want an isomorphism from GA to A such that a co-cycle condition is satisfied. I mean, for the trivial group element, we want it to be the identity, and then the co-cycle identity is hopefully this one here. Okay, and morphisms are, the only thing they can be maps on the A's that are compatible with the extra structure. Okay, and if we think about it this way, then what I called this one category is these kinds of fixed points with respect to the trivial action. Right? If the action is trivial, then psi G is just an isomorph from A to A, and this condition just says it's compatible with,
So you don't want to think about this fixed point category as some like localization of A. You want to define it in this form, I guess.
I want to define it exactly like this.
Okay. Well, I mean, when you want to make things isomorphic that weren't isomorphic before, I guess the way I'm used to is you just add the.
No. That's different. That's different. This is right. This contains the actual fixed category as a subcategory, right? But it's bigger. It's sort of only up to homotopy fixed points, right? Whereas these things, these I think we should think about as quotients, right? A quotient category. But because here we just added the isomorphism, but it's a different construction. Okay.
Well, psi G is not being added.
But
that happens to.
Right. Psi G is right. Psi G is not a new player. Right, psi G was, so this is an iso in A, right? It was there before, but we sort of put it together with A to then form an object in this quotient. Okay, good. Right, I did this. And then maybe we should. Let me erase this. Okay, so transfers. So, and the first version I want to discuss is the fact that, so the K-theory of this acts as maps on the K-theory of group rings, which we can formulate as follows. So we take an additive category and then the corresponding group ring, couple it with this homotopy fixed point category, this one category in this case, and I get a functor G, which we can write down. So, right, I have an object in A, those are the objects over here, and an object in here, that was a V together with an action, and I'm just going to take the tensor product of A with V. We may have to make a little decision here, but basically V is just Z to the N. So this is just another name for A to the N. N-fold sum of A. Good. And now I want to discuss what happens on morphisms, and to simplify it, I'll only have a morphism on the A part. Okay, so here the morphisms were finite linear combinations of morphisms in A, right, indexed by G, and the thing before G, phi G, was a map from AG to B. Okay, and then, so this goes to V tensor V. And now I need a map here. And I'm going to call it the transfer of phi, right, depending on V and psi. And it's, again, right, it needs to be a formal sum over the G's. And we need to figure out what is the coefficient at G. And we're going to take phi G tensor psi G. Okay? And if we sort of forget for a moment that the action on this category was trivial, then this is really the only thing we can do, right? We need something from G of A tensor V to A tensor V, but this is GA tensor GV. So the natural thing to do is to take the phi G that mapped, this is a B, sorry. That mapped GA to B, and then we need to map GV to V. I mean, if we remember that the action is trivial, then we could have taken the identity, but if we sort of don't remember this, then psi G's are all the options. Okay, so that's sort of the first instance of the kind of map I want to use. And so we get a transfer map depending on this object in the Swan category. On the group rings. Okay. Pardon? Sorry, I mean, I need to, if I define a functor, I need to define, right, the image of phi under the functor. And I mean, with the phi, if phi goes from here to here, then I need to define what it does on the images. I think
what we're asking the objects and the tensor product.
Pardon? What? Sorry, I think I misunderstand the question because it sounds. Right.
Object in the tensor product has two categories, which is phi.
Oh, right. That's maybe I mean that's not. I mean, is that better? I mean, it's right. We're defining. I mean, really, all I've done is for every object in here, I define the functor. But really, you get a bilinear functor, and then if you want, yeah. Okay, good. Thank you. Okay, and now we're going to improve on this slowly. Maybe not. Anyway, okay, so version 2. So now I'm still going to start with AG, but I'm going to replace the Swan category with this one, right? I'm just going to add the E to the free modules, to the free abelian group. So now they're spread out over E, and since G acts on E, we have an actual action, and now we really need to take some. Now this really makes, I mean, it made sense before, but now it's, right? Now we couldn't define it this way. It's no longer an action, it's a trivialization of sort of the orbit. Okay, and we're going to go to, right, putting in the E here allows us to go to here, to have the E on the other side as well. And the formula is very natural. So I have an A, and maybe if you don't like the tensor product, I'm going to write the times. Now, right, objects are more complicated. They consist of a T, a set, a row, that's the maps that were called pi, and the V, the maps to the free abelian groups. And then in addition, this data psi, this trivialization business. So that's And we're going to map it to. So now, over here, we need a set. Of course, we're going to take T. I'm going to use rho to map it still to E. But now we can change the way we map to, right, I mean, we need to change the map to the objects because now we're going to go to the objects of A, not to the objects of Fz. But there's a canonical way to do this. We just take the formula we had before. We take the tensor product pointwise. Okay? Okay, good. And let's spell out what happens if I have a morphism. Do I want to spell this out? I think I do. I mean, actually, right, I mean, there's only one formula that's going to make sense, and that's going to be the formula, but nevertheless, since I worked it out, I'm going to tell it to you. All right, so it has to be of this form. Right, that's the definition of morphisms in there. So I need to tell you what is the transfer of phi at G. Okay, now that's a morphism in A of E. Right, so it's something that has an entry for every pair of elements in T. Right, it's always going to be the same T. And then there is now only one way to write down something sensible. It's phi G times psi G. Right? The psi was a gadget in here, so it has this sort of form, right? It is a matrix, and I can use this matrix. Okay, and then an easy fact is that ultimately we're interested in how this behaves with respect to control in E. Right? I want matrix entries to be 0 when they move a lot in E. But this translates directly from the corresponding questions about psi. Right? I mean, psi is the only thing that shows up here and moves in the T direction. Okay, so if the psi G are all epsilon controlled, then the phi, I call it transfer now. Transfer of phi is also epsilon controlled. Okay, and slightly better, we only need this for all G with phi G not equal to 0, right? I mean, phi only has finite group elements and the other ones don't show up, so, right. Okay, and then it's now straightforward to do the same thing on the D0 guys, because those were just products of these AE guys, and I can just, over each natural number, I can use this functor. Okay, so, or this construction. Okay, so the final version of this. Now, we're going to start on the left-hand side of the map we're interested in. Take the tensor product. All right. We also replace the F guys with this product version of it. And instead of taking the group ring, we take these fixed points. And then go to where we want to go. And it's just so if I have an S, a pi, and an A over here, and then T, rho V. Right now I think of it as an object in here. It also comes with a psi. I need to say, where do I go? But I just, I do the same formula as I did over here over each n, right? So formally this means I took the product of S times T, but over n, right? Both come with maps to n, and I want those to be the same. Then I need to map S, comma T to E times n, and I'm going to do it by just taking rho of T, right? I mean, S only has a map to n, and I already know what S of n, what S in n is because it's the same as T in n, so it doesn't need to show up. And on objects, we take the natural thing, we take the tensor product. Okay? And I'm not going to spell out what happens on morphisms. It's basically the same formula over there, right? I mean, it's just entry-wise we did before. So we get a transfer map for each of these T, rho V, psi, from the 0 point A, G. Okay. Okay, so that's good, but so this leaves us with the problem of finding suitable data here, right? In order to apply this machine, and this is kind of difficult, right? Because I mean, for E, we're going to put in this space for the virtually cyclic family of subgroups. In particular, it's not a finite space. It's going to be a gigantic space, and G is going to move around on it quite a bit, right? On the other hand, we said, I mean, over every natural number, I'm only allowed to take a finite number of entries, right? So the easiest way to produce a fixed point in here would be to produce an actual fixed point, right? To set over the same point in E, put the same module, right? Because then it would be actually G invariant. But that wouldn't satisfy the finiteness requirements. And then we need those finiteness requirements because otherwise, right, they won't be satisfied here. Okay, so there's some tension. We need to take a finite thing that is invariant under the group action up to these isomorphisms. Okay, so we can use the isomorphisms to move around a bit, but then as we go out to infinity over the natural numbers, the isomorphisms are not supposed to move around all that much. They're only supposed to move around a little bit. Okay, so this has the consequence that, I mean, we find that there are guys like this over here, but they will always use more and more modules over E. Okay, so let me write this down. So objects these T rho V psi will always all right, if I look, how much stuff did I use over a point, over one of the natural numbers? As I go out to the right, I mean, this goes to infinity as n goes to infinity. And in particular, we won't get an inverse. And at this point, we're interested in a right inverse to the map we want to. Okay, so, right, but there's, I mean, one thing we can do that makes life, that gives us a better chance, is we can use let me back up a minute. Right? I mean, if I have, if my module here is, right, if this V guy has a large rank, then it blows up the objects quite a bit, and it's not going to be the identity, right? Even for this first functor, right? If you want the identity, you would have to use the trivial module with the trivial action. Okay, and the trivial module with the trivial action we cannot get almost invariant over here, right? But we can do this in chain complexes. So we're going to use chain complexes, and let's say bounded, right? Then we have a better chance, because now a chain complexity can be gigantic, but it might still be contractible. And so in the K-theory, it does exactly the same as the trivial module. Okay, so with chain complex, we have a better chance. It turns out that one needs to be even a little more flexible about this. So one has to give up on the precise on this precise finiteness condition. I mean, the chain complexes we use won't be actually finite; they'll just be finite up to homotopy. Okay, but sorry.
You guys call them perfect.
Okay, perfect.
Could you explain again why you need more modules?
Okay, yeah, let's so this, yeah, so otherwise it looks kind of, okay. So here is E. Okay, and I have a point in E, and somewhere I have to put the first module, okay? But then I want it, right, let's say I just pick this one, that's at this point, okay? But then I need this isomorphism from, right, so the thing we started with was, let's be slow, if T was just a singleton, right, and then T, I mean the map to E is just, T is a point in E, and then we have this module V, right? Let's start with this gadget. And I want an isomorphism to G of it. So what's G of it? It has the same T. It moves the point to G of T, and then keeps the same V. Okay, so I need an isomorphism between those two. Okay? Well, but G of, I mean, so this is T, and G of T, I mean, it's going to be somewhere else. And the natural thing to do is to say, okay, I take the identity here. Okay? But, I mean, it's going to move from T to G of T. Okay? So, what would be helpful if I had, right, if I had two modules. It wasn't just 1 point, it was 2 points. Right? I had a T prime close to G of T. Right? And also a module, another copy of V here. Then I could say, okay, let's just identify those two. And then it moves just a little bit. Right, but now we need to arrange this in a clever order. Okay, I mean there are examples where you can do this explicitly, but it's kind of messy. Okay, right. So you need this one, but then I mean it's clear you need this for more and more group elements. You need more and more V's, and then you need to come back. And it's a messy, but it's a complicated thing. I mean it might be surprising if you first think about. I mean once you thought about this problem, it starts to be kind of dubious that there are any objects at all. But in fact there are, but they still all have this problem, so they won't do the right thing for us in K-theory, but then you do chain complexes and then you have a better chance, right? The chain complex might be huge, but still its homology might be just Z with the trivial action and it might be the correct map. Okay, let's see what I wanted to say next. Okay, I wanted to spell this out a tiny bit. Okay. Okay, so if let me just abbreviate this a little bit in, I guess I should put a star chain complex now. Oh, sorry. So, right, I'm going to restrict it to, I mean, these guys are spread out over E times N. I can restrict to every N, and can ask that here it is just Z with the trivial action in, and we can forget about the control. So it's just put back in the Swan group. Well, the chain complex version of this, right? So if here, over here, so if the thing we use looks over N like the trivial thing, once we project back to here in chain complexes, then the corresponding transfer is a right inverse. To D naught. Right? I mean, we use the transfer to go over here, produce all this kind of control, but then we project back and forget this kind of control, and then to see what happens, we can just compute over here for every n, and if for every n nothing happens, then nothing happened. Okay. And this is one point where it's helpful to have used this D0 stuff, right? Because otherwise I would have to, I couldn't just say I put over every n something. They would have all to be able to talk to each other because they were going morphisms the other way. So this simplifies this greatly. Okay. Okay, so we need to produce chain complexes, and the best way to produce chain one more thing. If I say chain complex, then I have now a further requirement. I have the boundary map in the chain complex. Right? It's also, again, a gadget over E, and it needs to be controlled. Right? But I told you how to produce controlled chain complexes over a space. Yeah? We just take the simplicial chain complex. Sorry, we take the simplicial chain complex of chain. Right, that's the simplicial chain complex of a simplicial complex. Right? Maybe after some subdivisions. Okay, and this is then used in the following theorem. That we proved with Wolfgang Luck and Holger Reich when we thought about hyperbolic groups. And it gives a general criterion. So let G be a group and F be a family. Typically, in the best case, it's the family of virtual cyclic subgroups, And we assume that we find an N and a compact contractible simplicial complex X, right? That's going to be the chain complex we're going to use. I want it to be contractible because it's supposed to be trivial in K-theory. It should come with a G action because we need this homotopy fixed point datum there. Such that in addition we find a sequence of maps from X to the space where we want to go, and there I want to stay in the n skeleton. Right? That was the condition I forgot the last time and mentioned at the beginning. So we have a sequence of maps. Okay, so this already is enough to give us chain complexes. We can just take the singular chain complex, the simplicial chain complex of X. Then it's a gadget over X, but with this map we make it a gadget over here. Okay, and then we want it to be almost G invariant over here, and that translates into that we want this map. Right, we already had a G action here that we could use to trivialize this chain complex. We want this map to commute with the G action, or to at least almost commute with the G action. Okay, so
There's a little n and a capital N, and the capital N is fixed.
right, right. This is the capital N, right, and this is so for all n. Thank you. So satisfying. So we'll need to compare right, whether or not Fn commutes with the G action. And again, by the same sort of discussion we had over here, we won't be able to find, this is a non-compact space, it's a big space, right? This is supposed to be compact. We'll never find a map from a compact space into here that's G invariant, right? I mean, it's just, I mean, the action just moves too much. But we have a chance if we're allowed to sort of correct this a little bit each time, okay? And this is what I write down here. So instead of having them equal, we're going to control the distance, and I need this to be uniform in X, but not in G. So I fix the group element. Basically, we can fix the group elements because at every point we only have to think about finitely many G's. But I need to do this uniformly over X, and I want this to go to 0 as n goes to infinity. Right? And this translates then into, if I take this simplicial chain complex, move it over here, then I can actually find these psi G's that are almost isomorph. I mean, that, you know, that translate between the chain complex and its G version of it by only moving a small bit. We have to exactly move by this much. Okay, and then the conclusion is that the assembly map is an isomorphism. Okay, I only discussed surjectivity because I only said right inverse, but then there are relatively easy tricks, or not so hard tricks, that do the injectivity part sort of by a similar argument or as a formal consequence of the surjectivity. Okay, and one thing is that, right. So this is an assumption that works, and that, and there are examples where you can, with a G action, but I should say with G action by homeomorphisms. Okay, so the G action will not be simplicial. And this gives us further trouble in creating the correct chain complexes. And this is where we actually have to start to say, okay, we're not going to work with finite things, but only with homotopy finite things. And moreover, one can relax this to say an ER, meaning a Euclidean retract. That's slightly more general than this, and sometimes it's better. It's convenient to have this. Okay. I want to point out one somewhat unpleasant thing about the assumptions in this theorem. Namely, I mean, so this here, it's not a fixed simplicial complex, right? I mean, it's just, I mean, if I say EFG, that's just a homotopy type. But the way I've written it, I'm thinking about extra points in here, so I'm thinking about a concrete model. Okay? But it's not clear to me, and I don't think it's true, that if I can satisfy, so that I find these maps Fn for one model, that then I will be able to find it for any other model, right? So it's not, the formulation is not very, very homotopy theoretical. It's really about this, an actual choice of this space that we can pick here. I mean, there's actually a canonical space one can sort of pick a model for EFG that has the best chance of getting these maps. Okay, but it's not, it doesn't then follow that it's going to work for any other thing. Which, right, if we think of, I mean, what we're trying to prove, that we get this isomorphism, and that's really more homotopy theoretical gadget, and if we picture here, it certainly does not depend on the choice of EFG. I find this a little unsettling. It would be better if our conditions would be more homotopy theoretical. But they're not, they're very geometric. Okay, and
once you have this one family of map of subgroups F, you change the family of subgroups, the hypotheses don't really change, and it says that the classifying spaces are independent of that. So past that point?
No. So, I mean, sorry. I put in an F, and it's true for an F. Of course, we're interested in the virtuous cyclic case, but sometimes you cannot do it for the virtuous cyclic case. I mean, the more isotropy you have over here, the easier it becomes to find equivariant maps. I mean, in some sense, the more isotropy you put in here, the smaller the space becomes. Sure. So the easier it's going to be. Then it's going to be easier, but then the conclusion of the theorem is weaker, because then it's going to be more complicated to conclude this. Okay, but maybe let me state this, because it's I didn't, and it's a very useful thing. Right? I mean, you're basically asking, so why? I mean, why would it be good to have this for the wrong F? That's sort of a natural question to ask here, and so there is a transitivity principle. So consider, and that's a very general thing. That's certainly in homotopy theory and not a geometric thing. So consider two families, one bigger than the other. Maybe F is virtuous cyclic and G is something we had to work with because, the geometry forced us to. Okay. And then, and assume two things. Assume first we get the isomorphism for the bigger family, but we're really interested in the smaller one. But assume also, so this is G, and this was Davis' look. Assume also if for all, I should have called this gamma for a second, and the notation is better. All right, okay, then for, sorry? There's one G left, thank you. Right, if suppose for all G in this bigger family, we know the thing we want to know already. Okay, then we get what we're after for gamma. Okay, that's the use of it. That's why it's useful to prove it first for a bigger family, because I mean it reduces you to considering groups in this family. And if you think about the statement, I mean if you believe in the slogan that, right, this being an isomorphism means I can compute this in terms of the K-theory of all subgroups in the family, then this makes perfect sense, right? Because the next statement says, for every subgroup in this family, I can compute relative to subgroups in the smaller family. And if I put it together, I should be able to get this. Right, exactly, very good point, right? Farrell-Jones implies Chang's conjecture is exactly by this argument where we use the family of cyclic subgroups and the family of the trivial subgroup, and then to get, then Farrell-Jones is sort of this statement, and we also need this, but this is then just for cyclic subgroups, i.e. for infinite cyclic groups, and then we just use Bartels-Swan and assume that our category is sufficiently regular. I mean, otherwise it doesn't work, right? I mean, that's exact, and that's, I think that's an important point, because this is the only place where if you go from these kind of theorems, right, to say the white-tailed group is trivial, or to these geometric conclusions about torsion-free groups. And the only place where you make use of the fact that your coefficients satisfy something, that they're better than anything, that they're regular, is really only at this point. Only when you use Bartels-Swan at the very end, there you use it. Everything else is completely general. Okay, good. Okay. Okay, so this maybe clarifies the use of F. Thank you. Okay, then let me just finish by giving you a list of groups where the assumptions of the theorem are satisfied. As already said, hyperbolic groups, and here F is the family of virtual cyclic subgroups, and that's the same paper. And we'll do the free group on Friday. Okay, we'll do it one instance of this, namely the free group. Okay, and then there are generalizations. Let me just say one. So the mapping class group of a closed surface. So this is the mapping class group. But it's also true, but now the family is bigger. It has all virtual cyclics, but also something that I'm going to say are mapping class groups, where Y has smaller complexity. It's not quite true. Really, the family is built out of those groups, but built out of in a way that's controllable, and that's joint work with Mladen-Bestvina. And then by this sort of transitivity principle, one gets the Farrell-Jones conjecture for the mapping class groups. And but not everything works with this theorem as formulated, so that there are generalizations of the theorem. And then one gets more groups. And one family of groups one gets in the end, where one has to do. Well, no, we can say one needs a generalization of this theorem, and again this sort of induction. Then one gets the Farrell-Jones conjecture for all lattices in Lie groups, and this is Kamaya Lück and Rüpping. Okay, and I think I finish here for today. Sorry? Yeah. I mean, actually, so Rüpping even, on the way to this, he proves for all subgroups of GL and Q bar. Well, the thing is true.
What about things like you take a curve over Q? Yeah.
Well, actually, I'm not fluent enough in this language, but maybe is this arithmetic groups? Maybe no. Okay, no. Then maybe the answer is we don't know. I mean, maybe you explain this in detail later. Then.
So maybe a follow-up to this. All of the examples that I think that I've seen, there's some underlying geometry that's going on here.
Absolutely, yes.
Where you don't have a good handle on the geometry.
Well, so let me say one more theorem where it's less clear there is geometry. So maybe, I don't know, depends on your taste. So Wegener, he proved the Farrell-Jones conjecture for all solvable groups. And then the criterion he uses, it can be phrased in this sort of language, but the way, here, maybe, okay, let me say this. So the way we check these conditions, for example, in the case of hyperbolic groups, strongly use negative curvature and are very much motivated by the way Farrell and Jones proved their theorem for negatively curved manifolds. Okay, but then there is another technique, a different sort of geometry that comes from Farrell and Chang, where they used maps into finite quotients and then used induction. So maps into finite quotients, but if the finite group needs to be big enough for their interesting induction results relative to hyperelementary subgroups. And then you can pull those back to the big group and can try to work your way down and combine this with a little bit of geometry. And this sort of argument strongly enters here. But there's still geometry. It's just less clear that it's just non-positively curved or the negatively curved geometry.
I have a more elementary question.
Excellent.
Trying to wrap my head around this, because it seems very hard to predict if you ever find such sequences of maps in the first place.
That's good. Yeah, I think.
Let's consider the case where the family F is just a trivial group. Is it true that you can never do this?
Excellent. Very good question. Yeah. The thing is, so if you have a fixed point for the action on X here, okay, you don't have a chance to move to find almost equivalent maps over here if there isn't a fixed point over here as well. Because, the fixed point, it moves somewhere, and then it doesn't move under the G's. So here, it's under the G's, it's only allowed to move a little bit. But on this sort of space, either I move. Well, I could, right? It could be like this. Right? I move like just a tiny bit over here. But then the reason for this was that there was a fixed point nearby. Okay, so certainly it's true if X has fixed points, the same sort of fixed points need to show up over here. And that's very nice because that's what I like about this condition. Because if you think about it, it immediately tells you that you need to work at least relative to the infinite cyclic. Well, actually, need to work relative to cyclic subgroups. Because, right, by Brouwer's theorem, any action on a compact contractible symmetric complex will have a fixed point. Okay? So it's never going to work with respect to the trivial group. And if it would, we would prove something that's not true. So this I like. Yeah. Thank you.
So that's why you can only prove Chang's conjecture by going.
Right. But it has to be this way, right? Because Chang's conjecture is only true for certain rings. At some point, you have to use the assumption on the ring. And these sort of arguments we do never use anything about the ring, and only it's used at the very end. And that's, I think, the reason why this is a beautiful split up of the conjecture. Even if you're interested in Chung's conjecture, the Farrell-Jones conjecture has the advantage that you don't have to, in your argument, somehow imagine a place where you use that your ring is regular, right? You can imagine this is purely geometric, and then only at the very end you use this. Yeah, thank you.